Hey kids, welcome to 2021. Woohoo! Happy New Year! New Year. Let's hope 2021 brings us back together at some point. All right, so remember what we were learning was the first fundamental theorem of calculus. And the big idea is that the graph that you are integrating under, the accumulation function, which is an integral function from some constant to x of f of t dt, has a derivative that is the very graph you're accumulating under. So when this says let little f be the function whose graph is shown at the right, so this is little f, defined between 0 and 2. Make note of when it's defined, right, where they're going to ask you to accumulate, between 0 and 2 included, has point symmetry about the point 1 comma 0. So think about what that would mean. If they're telling us the graph starts at 0, ends at 2, but has point symmetry around the point 1, 0, right? Think about that, what that means for accumulation. Those two pieces have the exact same absolute value, but the integral from 0 to 1 would be positive. The integral from 1 to 2 would be negative, but they would have the exact same magnitude, if you will, right? So capital F is the accumulator. Little f is the derivative of the accumulator. So as I scan each one of these problems, note that for A and B, I am just doing integrals, right? Calculate integrals. But for capital F, right? Capital F has a maximum value. This is of the graph I don't see. You don't see the graph of capital F. But this, capital F prime, by the first fundamental theorem, is the graph I'm looking at. This is asking me, capital F double prime is asking me about the first derivative of the graph I'm looking at. So whenever you are asked to draw, use derivative test info and calculations that you were asked to do to sketch. Capital F, the graph you can't see. All right, so let's just start. Evaluate capital F of 0. So notice that my starting limit of integration is 0. Right, 0. And they want me to go from 0 to 0. Well, you know, I don't care what my graph looks like, right? If you are accumulating 0 to 0, under any graph, your dt is 0, so your integral is 0, right? But how about going from 0 to 2? Remember, you're starting at 0, but you're ending at 2 this time. So they wanted me to start and stop at 0, but now they want me to go from 0 to 2. What's true? Even though I don't know anything, this is not geometry, I can't tell you what this is, but because of point symmetry, what do you know? Also going to be 0. Now, where does capital F have a maximum value? Have a maximum value, right? Maximum value is where the first derivative changes from positive to negative, or what? Now, I don't have, remember, what goes on your list of suspects? Where the first derivative equals 0 or does not exist. Well, this is the graph of the first derivative. It exists everywhere from 0 to 2. So I don't have to worry about where the derivative does not exist, but what else do I have to consider? Endpoints. Hello. And the other clue that I had to think about endpoints was up here in the directions. So our list of suspects are 0, right? 2 endpoints, and where the derivative changes from positive to negative. So at x equals 1, I'm certainly a maximum. What's true about the left endpoint? Left endpoint, the derivative is positive, meaning if your derivative is positive, what does that mean? Capital F is increasing. And if you're increasing from the left endpoint, you must be a min. How about at the endpoint 2? The derivative is negative, which means the original is decreasing. And if the original is decreasing to the right endpoint, the right endpoint must also be a min. So capital F has a maximum value at x equals. It didn't ask me what the maximum value was, and I don't know what it is, right? Because I don't know the integral from 0 to 1. But at x equals 1 is the answer to C. Where does F, capital F prime, have a maximum value? Right? So the goal of this problem is to try to make sure you know when to read the graph you're looking at and when to think for its heights and when to think about the graph that you can't see. So capital F prime is little f. The maximum value is right here, right? Put that in blue. Cap F prime has a minimum value at about 1.5. But do you see that I'm getting those values purely from looking at the graph of little f? Whereas for C, capital F is the graph I don't see. It's the one I'm going to end up drawing down here. Now, what does this say? The graph I can't see, the second derivative is positive, concave up, right? When is a graph concave up? Well, when its second derivative is positive, well, when its first derivative is doing what? So they're just asking where's the second derivative positive, where little f is increasing. It's supposed to be a square bracket. Hey, I'm using the values that they just asked me for in part D and E, aren't they? Now, this problem didn't ask right now, but I'm going to need this for my drawing. If the second derivative, right, is positive, where the first derivative is increasing, I'm going to be able to draw concave up pieces. How about where the second derivative is negative? That's asking about on the original concave down pieces. Where is the second derivative negative? When the first derivative is decreasing. Where is that? In between the concave up intervals. So using all of this information, they want me to draw a sketch of the graph I can't see. So I'm gonna erase this. So hopefully you have all this information down, and I'll show you what they want from a drawing. So they want the values that they gave us here. Oops, I need to do this in red, sorry. So capital F of 0 was 0. Capital F of 2 was 0. Capital F has a maximum value at x equals 1. The derivative is positive from 0 to 1. Therefore, the graph I'm going to draw is increasing, but due to the concavity issues, I know that I am concave up from 0 to 0.5. Concave down from 0.5 to 1.5. And then concave up from 1.5 to 1. Notice that when the first derivative is positive, the graph I drew was increasing. When the first derivative was negative, the graph I drew was decreasing. But where the first derivative was increasing, I drew concave up pieces. Where the first derivative was decreasing, I drew concave down pieces. Let me draw and sketch that a little bit better. Notice that the height of my maximum is up to you, right? I don't know the actual height of the maximum. What you're going to be graded on is this. Did you start and stop at the correct place? Did you have a maximum at 1? The height of that maximum is not going to be graded, right? I don't have enough information to know the exact height. And do you have your points of inflection that correspond to the places where your first derivative had maxes and mins? So as you can see, mine's a little off. Okay, let's do another one. Notice again, here's my accumulator function. And the function I'm accumulating integrals from is the derivative of the accumulator. So little f is a derivative. So notice that part A is asking me to actually calculate. What's different about this graph than the first example is that you've got geometry and boxes to be able to count. So capital F of 0 means start at 0, and tell me the integral from 0 to 0. I'll do that over here. Right? Going nowhere gets me 0. Capital F of 3, starting at 0, 1, 2, 3. That's going to get me this triangle and this triangle. I don't actually need to calculate their areas. I can see they're the same, so they will balance each other out, and I'll get 0. But what about capital F of 5? It's, well, I'm going to have 0, but I'm going to add, accumulate from 0, the area of this rectangle, which is just 2 by 3. F of 7 is going to take the 0 plus the 0 plus the 6 and give me this rectangle, triangle, and this triangle. But what's that? Those are going to balance each other out, so I'm going to end up back at 6. But what about F of 10? F of 10 is going to take the 0 plus the 0 plus the 6 and add what? This large rectangle, which is going to be a negative integral, and this teeny tiny little triangle. I trust that you will do that on your own and verify, but I got 3.5 when I was done. So these are all points that I'm going to plot when I get down to part D. Sketch the graph of capital F. They're going to want me to plot these points. So at 0, I'm at 0. At 3, I'm at 0. At 5, I'm at 6. At 7, I'm back to 6. And by 10, I'm at 3.5. Now look at B. On what subintervals, hey, notice 0 and 10 are included. Think to yourself, endpoints matter. Where is capital F? The graph I can't see increasing. Where is it decreasing? Explain. By the first fundamental theorem, capital F prime is equal to the graph I'm looking at. Therefore, capital F is increasing when little f is what? Positive. That's why. That's the explanation. When they've notice the first problem that we didn't ask me to explain anything, but this one is. So what they want is you to make sure to state the first fundamental theorem, and that's all you have to do. And then you do your derivative tests. So for part B, I just have to list, I've done my explanation up there, And the intervals are from, and you're allowed to just kind of guess here, right? So be nice to myself. I'm going to guess that's 1.5. And AP doesn't care if you make these soft brackets or hard brackets on turning points, so don't worry about that. But definitely include your endpoint. So that's increasing, and decreasing would be everywhere the first derivative is negative. Notice what is true about the derivative here. The derivative changes from negative to positive. Therefore, the graph I'm going to draw has a minimum. The derivative changes from positive to negative. The graph I'm going to draw has a maximum. At the right endpoint, the derivative is positive, meaning you're increasing to the right endpoint. Here, the derivative is negative. Therefore, you are decreasing from the left endpoint. So for C, where does F, the graph I can't see, have its? You need to know that its means absolute value, its minimum value. So my suspects are endpoints because they were included. And anywhere the derivative changed sign. I don't have a place where the derivative is undefined. Remember, and this is hard for kids sometimes. They're like, hey, wait, there's a point, right? There's a point, there's a point, there's a point there. It's not smooth. Truth. The derivative of the blue graph, F double prime, does not exist. At x equals, what is that? 1, 2, 3, 4, 5, and 7. But little f is the derivative of capital F. All you need is continuity, right? There is a derivative at every point between 0 and 10 on capital F. It has a derivative everywhere. The derivative of little f does not exist here, here, and here. Now, why do I care about the second derivative, though? I don't actually care where the second derivative does not exist. I care where the second derivative is increasing or decreasing. Because where the first derivative is increasing, the graph I'm going to draw is concave up. And it didn't ask me that, but I'm still going to sketch the graph. Wherever the derivative is first derivative is decreasing, I'm going to draw concave down. And where the first derivative is constant, I'm going to draw a straight graph, no curvature. So back to C, I have my suspects, but I didn't determine who was who, right? So x equals 0. Notice I know that that value is 0. At x equals 10, I know my value is 3.5. Notice that all of these places, I have a value except for 9.5. And 1.5, right? Oh, no, sorry, I don't have one for any of these, but I can figure them out, right? At 1.5, my integral is negative, and it's going to be more negative than 0. What's my value going to be at 6? I started at 6, right here at f of 5. 1, 2, 3, 4, 5. I was at 6, but by 7, so I have 6 plus my triangle. How about 9.5? I have a whole bunch of negatives, right? So I need to erase all of this while I start to draw our information. So hopefully you've captured it. So again, I have 0. At 3, I know I'm at 0. 5, I'm up here at 6. 7, I'm up at 6. And at 10, I'm at 3.5. We know that we are, since our derivative is negative, we are decreasing, and we have a minimum here. But we are concave up. Still concave up, but our derivative is positive, so we are increasing. Derivative is still here. The derivative is positive, but I have my derivative is constant, so I'm going to draw a straight graph, but increasing because the derivative is positive. Derivative is still positive, so I have to go up, but I'm concave down, where the derivative changes from positive to negative. I have a maximum. My derivative is negative, decreasing. Derivative is still negative, but now the derivative is increasing, so I need to be concave up. Derivative changes from positive to negative. So there is a minimum there. And then derivative is positive, so I am increasing again and increasing to the right endpoint. Because of geometry and my accumulation function, I can actually find these heights. Only because this was a graph made up of line segments, I can actually find the height of this. And I can calculate the absolute max and the absolute min. And I leave that to you. What you're going to be graded on, again, especially finding the heights is great, but really that is just geometry, right? I've got triangles, rectangles, trapezoids. The most important pieces that you're going to be graded on here is where you are increasing and decreasing, the intervals that you are concave up and concave down, the x values of your max and mins. That's the vast majority of your points. And when you are asked to explain any of those, always, always, always start off with the fundamental theorem. It is fundamental. And then you talk about the first derivative tests, which is old news. All right, last one. And again, if you want to pause the video and do this without me, and then come back and check and see what I've got. This time, notice they've abandoned the capital F. G has an integral in it. This is the accumulator function. It includes endpoints from -3 to 15. And the graph I'm accumulating integral values under is the graph I see. This is the derivative of the accumulator G. Notice this little twist, 5 plus an accumulator. Also notice, where do you start accumulating values from? So this is calculate. This is derivative tests. Well, it's a trap. Look at that, didn't see that coming, did you? Trapezoidal approximation, because notice that even though they've given me boxes, I cannot actually integrate this. I don't have any equation, and I don't have exact geometry to be able to integrate. So they're going to ask me to approximate, and they told me the way they want me to do it is the trapezoidal rule. But first, they do want me to find some values, right? They want me to plug and chug. So they want me to go to the function g and plug in 6. So g of 6 is actually accumulating, not using the derivative. And for x, they want you to plug in 6. So what is any integral when you start and stop at the same place? But don't forget you have 5 here. Right? So g of 6 is equal to 5. They don't ask you for any other accumulation values. They just ask me for the derivative. Well, what is the derivative of g? G prime of 6 is, by the first fundamental theorem, little f of 6. Just read your graph. What is it? Then they want g prime of g double prime. Well, g double prime of 6 is asking you for little f prime at 6. What is the derivative of the graph you're looking at 6? Hello? 0. Cool, right? Now it asks me on what intervals is g, the graph I can't see, decreasing, and they want me to justify my answer. Before I even answer the question, I'm going to do the justification. I'm going to say g prime is equal to f, therefore g is decreasing when f prime is what? Negative. There, right here. Done and done. On what intervals is the graph of g, the graph I can't see, concave down? I'm going to do the justification before I even answer the question. I know it's when f double prime is equal to 0, but what does that mean for f double primes, right? The graph it came from, when the first derivative is doing what? Decreasing. And I can see where that is. This problem did not ask me to graph. So they're not asking me to graph the original, they're just asking me to approximate the actual integral. So again, so I'll go up here and do part D. The actual integral, not G. They're not doing this 5 plus, right? Is approximately the trapezoidal rule using 6 subintervals. Delta t is equal to 3. So remember, the trapezoidal rule is delta t times a half and notice that each one of these subintervals, that's a 3, 3, So I have 1, 2, 3, 4, 5, 6 trapezoids. And I'm going to use the left endpoint once and the right endpoint once. And then 2 times all the middle. Let's just see. So bad. Didn't realize how bad that was as I was writing. Okay, right, the trapezoidal rule uses the left endpoint once, the right endpoint once, and then all the middle values twice. When I was done with all of that, I got 12. Okay. All right, so what we're going to ask you to do is to try the next problems on your own and see how far you get. And in our live session, we will go over the grading of these and what AP wants to see from you. And I will see you in our next live session.